to understand then the relationship between this energy E and the behavior of my solution as I go out towards positive infinity, what I've done is I've made a movie in which we can look at these solutions as we've written them down and how they behave then as a function of energy. And I will begin the movie with low values of the energy right near the bottom of the potential well. And energy is very close to zero. And then I will be increasing the value of the energy. And just to recall, remember what we're expecting before we look at the movie. We're expecting that as we increase that energy, we will be decreasing the amount of curvature away from the axis in the forbidden regions, while at the same time increasing the amount of curvature toward the axis in the classically allowed region. So let's take a look at what this function will look like when the energy is very close to the value at the bottom of the well. So our solution at that point would look something like what we have presented to you here. So what I'm plotting here on this axis, this is just showing you what that wave function looks like. And on the horizontal axis, I'm plotting the values of x for you that you can see down here along the bottom. And now, and the other thing you can see is that in this region, right, I'm curving, it's hard to see, but it's actually curving away from the axis until I reach about this location, which then is where I enter into the classically allowed region. And notice for the classically allowed region right now, the wave function is almost perfectly straight. And that is because I've put an energy that is right near the bottom of the well. So that wave vector k is approximately equal to 0 in that range. So I've got no curvature. It's basically a straight line. If you looked very closely, you might detect actually visually there's a little bit of downward curvature in there. Then what happens is that this curve enters into the classically forbidden region, which begins somewhere around here. It enters in then with the appropriate value and slope, but once it enters, because it's entered now with a positive value and an upward slope, and I have to continue always curving away from the axis, I end up with this type of exponential divergence. And we've already ruled this type of thing out as a possible state. And we had discussed this type of behavior in the past. Basically, it ends up giving me a wave function that is exponentially divergent. It's not normalizable. The other way to look at it is that if you did somehow manage to normalize it, all of the probability weight would be for a particle sitting at the very edge of the universe, and that's not the experiment that we're doing. So in this case, we could validly then rule out such a solution. Now, although I hope that this seems to be clear, but it does tell us something very fundamentally important fact. And that is one of the first quite general lessons we can draw from all of this that would have to hold for any type of bound state calculation. So here are a series of lessons I'll be writing down, and these are quite general in nature. So the first lesson I want you to notice is that I need some kind of downward curvature in my solution. In the solution I showed you here, there is essentially no downward curvature, and if I'm always curving away from the axis, well then there's no way I'm ever going to be able to avoid this kind of exponential blowing up. So therefore, I need the energies for any bound states have to fall in a certain range. So here is the energy for any type of a bound state. It has to be more than the minimum value of the potential. If my bound state energy, if I was thinking of a bound state and it had an energy that was always below the potential, well then I would never have any downward curvature and I would end up with that kind of divergence for sure. So it has to be greater than the minimum value of the potential, and that is the global minimum of the potential that I'm talking about. So the minimum of V of x over all possible x, which I'm defining that minimum of V of x as V min, and any bound state energies have to be less than that. And what's nice now is that we now have a nice bracket of where we can search for bound states, because we also know the bound state energies have to keep us out of the scattering region. So the energy has to then be less than the potential as I go off to plus or minus infinity in both directions, which means it has to be less than the minimum of those two choices, namely whether the minimum occurs if I go to plus or minus infinity. It has to be less than both of them. So we've learned now this first key lesson.